when we're dealing with beams and columns, very important that you go back to your fundamental of structural analysis and you find the table that corresponds to these figures that I've given you right here. These are statically indeterminate systems, and these form the fundamental values that you really need, and it's all you need to compute all your stiffness coefficients. Okay, what I have here is your stiffness coefficient is the definition of a stiffness coefficient is the force at degree of freedom I, so K sub ij is the force at degree of freedom I due to a unit deformation at degree of freedom. There shouldn't be no j, it should be degree of freedom j, while keeping all the other degrees of freedom equal to 0. So here's an example, and these are the two basic systems, okay? This is fixed at one end and pinned at the other, and this is fixed, okay? Because most of the time we're applying unit displacement or unit rotations, and so these are the two fundamentals that you need. Then everything else here is extras that can help you to just kind of make things faster and easier. And what I did is, on the bottom left, I gave you what I got online that gives you for most cases. I hope that these look familiar to you guys. And what I've done from those is I've selected the most important ones. I believe this is really the one that you should memorize most comfortably. And then in some of the exercises, we're also looking at this one. This one here can be derived from up here, just like this one can be derived from here, but it's just easier to memorize or learn those. I recommend that you memorize these terms through use. You will end up memorizing them, or always just write them down and have them in your cheat sheet whenever you do some sort of exams or something where you can carry those values with you. At some point you kind of start getting familiar because they're not that different, because K sub ij is equal to K sub ji. The stiffness matrix is symmetric. So look at this. We got 6EI over L squared and 6EI over L squared. So those are the ones that you really need to learn. Because this is symmetric, these two values are the same. And same with this 6EI over L squared. So what you're left with are 12EI over L cubed, 6EI over L squared, and then you got 2 and 4 EI over L. And so it's tricky to remember the L's, but then it's like, oh wait, this is a moment due to a rotation, this is a rotation due to a displacement or to a force, and vice versa, and then this is the displacement due to a force. So it kind of works out in recognizing what the degrees of freedom are. Okay, these are very important because these are the K's that you'll need in assembling a stiffness matrix in a multiple degree of freedom system. So you're not going to need these right away, but some of these are important. So for example, in many cases when we're dealing with single degree of freedom systems, we're going to be looking at cantilevers. So it's very important to know what is the K term for a cantilever. What is the force corresponding to a unit displacement, or vice versa, what is the displacement corresponding to a unit force? So here's a relationship between force and displacement. The K represents a unit displacement, so it's really the inversion of the delta here. Okay, so I just kind of wrote these on the right hand side for you. So this is a simply supported beam with the load in the middle, and that gives you what the deflection is, and therefore if you have a unit displacement in the middle, this is the force that is needed for that. So you can go vice versa on these and invert them. As I said, it's the force at the degree of freedom due to a unit deformation, or the inverse of it is the deformation due to a unit force. Okay, so one's flexibility and one is stiffness. Important that you get familiar with what each one represents. And so this graphic here, I recommend you sit and you maybe spend time understanding what these different quantities represent. I will go back to this when we do multiple degree of freedom systems. The way these are derived is using the principle of virtual work, probably principle of virtual displacements. I am not going down that path. And so these are values that you want to just memorize and maybe go back and figure out how these values came about. It's actually really cool on how they're done. So I recommend it. It's not so hard because the over-constraining is not that many degrees of freedom. So it can actually be done relatively easy. But these are the terms that you're going to refer to as you go through homeworks and exercises and through the class. So here's my example that are actually problems from the textbook. So now what I want to know is, what is my equation of motion, but really what is my stiffness? So the question is, what is K here? It's undamped, so once you have K, then you've got the mass and inertia. Now, what you want to first keep track of, this is weight, so the mass is going to be the weight divided by G. Now, look at this. This is, you know, a mass on top of a beam. So if this degree of freedom is my degree of freedom to the right, no, that's not really what I'm interested in, right? It's not going to slide. So my degree of freedom is actually in the vertical direction, okay? And it's actually shown in this figure here. There's U here, there's U here, and there's U here. All right, so what you want to do is you want to draw the deformed shape and impose a unit displacement in the degree of freedom that you're interested in, and you say, okay, what is the force that is needed to impose that unit displacement while keeping all other degrees of freedom 0? Well, I don't have any other degrees of freedom here, and that's why I'm looking at a simplified model here where I've got the cantilever. So here's my cantilever, and not cantilever, simply supported beam. It's going to deflect here by a unit displacement. Well, if we go back to, and I'm cheating and I'm putting here, that delta is equal to PL cubed over 48 EI. Therefore, K is equal to, setting this equal to 1, and what is P? So P is equal to, K is equal to 48 EI over L cubed times delta, which is 1. So K is 48 EI over L cubed. Okay? Second case, I have a cantilever. My degree of freedom is downward. So now this is delta. And if I look here, delta is equal to PL cubed over 3 EI. Therefore, K, which is equal to P of delta equal to 1, is equal to 3 EI over L cubed. Okay, well, those were easy ones to do. Now we got to do the last one, which is a little bit more complicated because I do not have this diagram. You can look this up, and I bet if you go online you can find out what is the deflection at that degree of freedom. But I'm actually going to sketch it out. So I have fixed and fixed. So what this is going to look like is difficult for me to draw. Something like this, where this is 0 slope here. And what is this deflection? Well, this guy here, where this slope is 0 here, is really half of this beam. Okay? And I know that the deflection, the force that it requires to push it down, is equal to 12 EI over L cubed. Okay? And so, but this is L, and here, this is actually L over 2. So I require 12 EI over L cubed, and this is 12 EI over L cubed, but this is actually L equals to L over 2. And so if we plug that in, so it becomes, I have very little room here. And so if L equals to L over 2, then 2, because I've got the total F, which is equal to K, is equal to 24 EI over L over 2 cubed. Well, 2 cubed is 8, right? And then now that's going to be up to the front. So 24 times 8 is equal to 8 per 8, 64. 8 times 16, 17, 18, 19, 20, 21, 22. 224. Wait, what am I doing? It's not 6 times 4, it's 8 times 4. Okay, so we have 24 times 8. So 8 times 4 is 32. 8 times 2 is 16, 17, 18, 19. And so K is equal to F is 192 EI over L cubed. I can't write anymore. Here's one stiffness, here's the other stiffness, and here's a third problem. Okay, so what I want you to do, I think it'd be great to go through these. This is basic structural analysis still. It's kind of a review, but I know a lot of people haven't done this type of exercise, but it's really important to go through and review what I did in each step here. Try this on your own and see if you get the same answer. If you don't, try different ways and see if you can get to the right answer. This 192 EI over L cubed is something you could even find in the textbooks, but I thought it would be a good opportunity to kind of just show you how we can compute it if we don't have it from a table. Okay, so I hope that this was a helpful exercise in just trying to go through this and not making it seem like such a simple concept.